DE-CTR Tech Talk series. Today, we are delighted to have Dr. Kézine Dysart from Nemours DuPont Hospital for Children to give us the first Tech Talk of 2024 on the application of supervised machine learning in predicting blood gas results in infants with severe chronic lung disease. However, before I introduce him, let me mention some housekeeping issues. We continue to provide CME credits for our Tech Talks and our ID series presentations. So we will distribute the information via email to those who registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Deborah Rees, and her email address will be posted in the chat box today. Upcoming events, we are still aligning our speakers for 2024, so please stay tuned for more information in the coming weeks and check your emails. So again, I'm really delighted to introduce Dr. Dysart today. Dr. Dysart is a Division Chief of Neonatal and Perinatal Medicine at Nemours Alfred DuPont Hospital, and also Professor of Pediatrics at the Sidney Kimmel Medical College from Thomas Jefferson University. He obtained an MD from Hahnemann University and did his residency in pediatric medicine at Thomas Jefferson University, as well as DuPont Hospital for Children here, our own hospital for children in Delaware. He obtained a fellowship in neonatal and perinatal medicine from Thomas Jefferson and Christiana Care Health System, and also a master in biomedical informatics at University of Pennsylvania Perelman School of Medicine. He has a very large number of publications and is a very sought after speaker regionally, nationally, and internationally. So we are really honored to have Dr. Dysart today to give us this presentation. Thank you.
Thank you. That was incredibly kind. I'm really excited to be here. Thanks for having me. As Claudine said, I'm a neonatologist and I take care of babies most of the time. I spend a lot of time thinking about how to use the data we collect. So I will talk today about a project I did that before I transitioned from CHOP to Nemours as part of my master's program. And I'll provide some clinical context. I want to just talk about a few things. One, the application of the supervised machine learning methods beyond just logistic regression, although logistic regression is one of the three I'll talk about in this talk. And then how how to try to improve prediction with those models with just hyperparameter tuning. And then I'll discuss an oversampling technique at the very end. And I hope you find it useful. And I'd love any feedback as I continue to work on actually this data set, although it's older now, and conceptualize how to use data sets that will be coming to Nemours soon as we collect more and more of this data systematically. So just to give you some introduction as to the problem, infants that are born preterm, less than 37 weeks, continue to suffer from pulmonary morbidities. Their lungs just aren't ready to be here with us. And the very therapies we use to save their life continue to increase injury, if you will. And the smallest babies born less than 1,000 grams continue to suffer mortality ranging from 10 to 50%, which is incredibly high at the smallest birth weights. I always give people the context of acute myelogenous leukemia or acute lymphoblastic leukemia, ALL is a better example, is a disease that if anybody, your child would have, is a shock. The survival rate for ALL for most children is far greater than being born 26 weeks or less. And that is still something we struggle with. Amongst the survivors, there's this disease called bronchopulmonary dysplasia that is a problem. It is characterized by continuing to need respiratory support at 36 weeks post-conceptual age. And amongst survivors less than 28 weeks happens about 40 to 50% of the time. So it's a big problem for us. A while ago, I was fortunate to be one of the investigators to try and come up with a better definition of BPD. And several of us at the time were like, we should use better methodologies than just expert opinion, which was really the current definition when we started this project, for which you see this complicated table, which I'll take a minute to try to explain. we really wanted to assess with just data we had available about patients in a structured data model called the Neonatal Research Network's generic database, which collects a structured amount of data about every baby born in any of the participating neonatal research network sites. The data here is for all babies less than 1,500 grams. I'm sorry, you can hear that in the background. I'm getting clinical text, but someone's covering that. And in this network, you collect this structured data. So we said, look, we'd really like to use that data to better assess some of the immutable characteristics about you that we know are associated with the outcome that I've already alluded to, like gestational age, birth weight, sex, being small for gestational age, meaning you are smaller than 10%, you're in the lowest 10 centile, say. Whether or not you got antenatal steroids, which we won't talk about here, treatment with magnesium, other cofactors we know can either raise or lower the risk of BPD. What was your required respiratory support at 36 weeks post-conceptual age or post-menstrual age? And we defined it in a variety of ways. Actually, there was 18 total combinations and a variety of grades. And we were looking to see how accurate could we be in predicting whether or not you would go on to die later in your life, or have a severe respiratory morbidity, which was characterized, or have a late death or moderate to severe neurodevelopmental injury. And it turned out that using data and using, this was a logistic regression model, that the most simple definition was the most predictive, which was reassuring. And we had only 3 grades, and they were simply based on clinical heuristics, actually, which support some of what clinicians already know but can't quantify mathematically. And so we took this, and this was published a while ago now. We also then looked more in a detailed way into the outcomes by our graded definition, just to see the acceleration, if you will, or the increased risk play out in real life. So you see across almost every column here, as you move from having no BPD, which was not the majority of the population you see here, it's actually the minority of the population. From grade 1 to grade 2 to grade 3 BPD, almost all of the outcomes we as clinicians are interested in are worse amongst the cohort that had the worst BPD, as characterized by having the need for invasive ventilation still months after your birth. And so this was sort of our first foray into, well, what could we do with this data? What could we predict? And how could this potentially benefit medicine? This was a more simple model. Like I said, this was sort of my entry point into, wow, this is really cool. This has led to, though, in subspecialty children's hospitals like CHOP or Nemours, teams evolving just for patients with the worst version of this disease. At CHOP, there is a team dedicated to just these patients. They care for about 30 to 50 infants a year. All the patients are on one care team, consistent group of caregivers, attendings, advanced practice providers, with a consistent set of heuristics in care management. And so this really forms the backdrop of who the research I'm about to tell you about was done in. I'm going to talk about high frequency data. I'm not going to talk about heart rate data, but this was really the first foray for neonatologists into using higher frequency data collection to predict something. So this work is essentially famous at this point. It has led to a monitor that will display this information called the HERO score. The primary hypothesis of this research was that heart rate characteristics would be predictive of your risk of death amongst those that had eventually, the subsequent works here would be about sepsis. And this represents that in a randomized controlled trial. These researchers continue to pursue this line of research, looking at heart rate characteristics, again, playing off the clinical knowledge that the loss of heart rate variability is incredibly poor. If it's fetal heart rate monitoring in the clinical setting, we know that a baby who loses heart rate variability is a baby under stress. And this was playing that forward into the neonatal period. And sure enough, there was a small but significant improvement in mortality amongst those being monitored for a change in heart rate variability. Interestingly, I was just speaking to some of the people who have taken on this work and moving it into the future, and it really hasn't been adopted widely throughout neonatal medicine. There's a variety of reasons why it might not have reached an implementation point or been taken up aside from the complexity, but also, and this is the first time I'll advance this concept, the positivity is not amazing, meaning that, and this is something we struggle with across the board, whether it be the calculators developed from the BPD definition I showed you, we have a sepsis risk calculator at this point, or this risk, is there's still a minority of patients who become positive with scores like this that actually have the disease of interest. And so there's a lot of false positives, if you will, and a lot of what I talk about when I work through how I work through my project and different hyperparameter tunings, trying to improve that, and where, frankly, to spoil the end, it didn't work out great. So that allows me to set the background and move into what we did. Between the time period of June of 2017 and September of 2019, every conventional ventilator in the newborn intensive care unit, the Children's Hospital of Philadelphia, was connected via medical device integration system at the head wall to a background clinical data warehouse. We were moving towards developing our own solution for clinical device integrations and the data that comes from them. It was time-stamped and stored in a Hadoop cluster identified by medical record number and room, which allowed us to re-identify data that was collected for certain patients. Blood gas values are obviously drawn for this cohort of patients. If you're on a ventilator, clinically, we need to know how we're doing. How is the minute ventilation we're providing you supporting you, and what is the result? And blood gas tensions are how we achieve that. We look at things like your pH, your partial pressure of carbon dioxide, to say, okay, that's good, we did a great job, or no, that's bad, we didn't do a great job. And so we looked specifically, we said, well, look, if we have this, we know we have a consistent care practice for a cohort on our chronic lung disease team. We know lots of those patients were ventilated. So why don't we look at the patients who were ultimately discharged from that team and see how much data we have in the clinical data warehouse from their ventilators, and if we can time sync it with blood gas values that were drawn. We looked at the ventilation values first from the medical device integration. 64 individual parameters were being reported to the clinical data warehouse every 5 to 6 seconds. We then used our own domain expertise to select values from that 64 parameter list that are indicative or of minute ventilation, the support we're giving you, or changes thereof as potential features to put into models. And then we developed time-lagged calculations for each of those, meaning what was the 10-minute average before an event, a blood gas value, a 60-minute average, and a 240-minute average median count, to say, okay, to grab short-term and long-term data grabs about the ventilator leading up to an event, which was the collection of a blood gas. Because it became the blood gas that we were interested in pairing with those ventilation periods and saying, can the ventilator and the values being collected by the ventilator predict the blood gas itself? Now, why would you ask that question? Because clinicians often can. We have learned heuristics that are if then else statements, as they are, that would say, well, if this part of the ventilation parameter has changed in this way, it likely indicates that the blood gas is either poor or acceptable or good enough to make a change and wean a patient from support. We ultimately created a label, a categorical outcome based on the pH and PCO2 values that we know, again, are associated. Now, I will say I did use some data science here to look at distributions of both the pH and the PaCO2, and I'll get to that in a second, to come up with the outcome, and both needed to be true. It wasn't either or, you had to have both. Most clinicians would agree that if your values are at this threshold or worse, that it's a problem, but it's interesting the data supported that eventually. The included infants were, as I said, all of those discharged from the multidisciplinary team with severe BPD. The restriction of that population allowed us to go for a homogeneity and management of the study population, but it reduced the number of infants who had been reported from that team from 69 to 31. We did feature engineer significantly from there. We developed a measure of change for each of the features. So for respiratory rate, say it might reflect moving from a low rate to a high rate, or a normal rate to a high rate, going from what's normal to Kipnick would be the word. And ratios were created for the short-term trend over the long-term trend. And then we examined those distributions, and any value above or below a standard deviation was considered to be abnormal. And that allowed us to say, wow, this is a deviation from the norm. Your short-term trend is no longer reflective of your long-term trend in a positive or negative direction. We picked the negative directions to say they were abnormal. Again, with our domain expertise. And this is how people manage the ventilator. You get called in the middle of the night because a patient becomes tachypnic and their minute ventilation is no longer appropriate. Can you come see the baby? It usually aligns with a clinical picture as well. And so that was a lot of what we tried to do here, is essentially prepare a data set that had features engineered that were consistent with what clinicians were seeing, interpreting from the data already being reported. We had a final feature set that was developed from the combination of the short and long-term trends and the 10-minute average, and the labeled value of the ratio for short and long-term trends is a categorical. For the purposes of this talk, I'll just talk about the 3 models that we started with, which were naive Bayes, logistic regression, and a random forest classifier. The random forest classifier often wins in any modeling. I think boosted trees would be a strong competitor, and it's currently running in the background, actually, of a different computer. Hyperparameters were tuned. Here chosen were max depth, the estimators, and the max features with a randomized search. We attempted to improve modeling through interaction terms added with different models, and then feature selection via selected K's best approach. And then we use K-cross-fold validation in conjunction with a score to report the mean area under the curve for the models and their abilities to predict. It included all of the 3 major languages you might think: SQL, R, and Python for the data extraction from the Hadoop cluster, and a CHOPS clinical data warehouse. Myself and a data analyst that was working within the CHOP neonatal division did the coding. For the work done in VS Code in Python, we used NumPy, Pandas, Seaborn, Matplotlib, sklearn, and stats models, as you might otherwise expect for this sort of work, but these are the tools we used. And then a lot of time went by. We learned a lot from our data. We learned a lot about what was working, what wasn't working, and I'll show that to you here. During the study period, there was actually 29,516 blood gas values recorded across the entire NICU. CHOPS NICU was quite large by then. It was moving from being somewhere in the range of 80 to 100 beds. And there's a lot of blood gas sampling that goes on. Amongst those blood gas samples, 5,000 were done amongst babies on the yellow team across 69 infants. Of those, 527 were missing, and 4,000 didn't match any ventilation data. That seems like a lot, but it highlights that the grand majority of patients, even with significant moderate to severe BPD, are not on a ventilator. And so it's only really the children with the worst disease, as you saw, it might reflect on the tables I showed in the background, that are stuck on ventilators beyond 36 weeks post-conceptual age. The majority are not, and so they were excluded. We ended up matching 952 blood gas results amongst 31 infants. Each blood gas result was considered to be a unique event, so there is repeated measures here, but we let that to pass for the initial forays into all of this. The demographics of those infants were exactly as we thought they would be. They were born about 25 weeks post-conceptual age. They were about 600 grams. CHOP is a referral nursery, just like this one. So they were admitted on or about day 72, but a huge deviation there, as is often the case. These infants had incredibly long lengths of stay. Again, very expected for this cohort. There was slightly more biologically male infants than female. Again, that's expected. Biologically male infants have worse lung disease when born premature than biologically female. And the majority of the infants were sent to a pediatric floor for discharge or a facility. Only one infant died during their hospital stay. Just want to show you some distributions of the values just to give you a sense of the realness of the data, and also to give you some sense that, and it gave us some sense that the data we had collected and were able to extract from the clinical data warehouse was indeed what you'd otherwise expect. These were our first sanity tests to say, could we do it? A lot of this project, if I'm honest, started with can we? And a huge part of the project is the extraction itself, which is non-trivial, as many here know. But this is exactly the blood gas distribution you'd expect to see for babies in this cohort. There is a tail to the left, as you see, as expected. It's almost not possible to be much higher than 7.6 there. It is possible to be much below 7. And so it is a non-normally distributed value, slightly with a small tail to the left, and it's as expected, which was reassuring. Again, if you look at the blood gas CO2 tensions, you see a sharp delineation there to the right, truncated in the distribution. That's because the machines won't report if the value is over 95 often. Our normal partial pressure of carbon dioxide, just in case, is about 40. 60 is not great. For an adult, 80 would be wow. 95 and 100 above is really something babies tolerate and survive way more than adults. Babies, that's why I'm a neonatologist, are far tougher than adults. I might have to be better at this. They are amazing to have the privilege to care for, and they tolerate things that most humans will not. So this is, again, the expected distribution. It really is pretty normal with that truncation there because of the fluke of laboratory testing. We dealt with that by re-engineering that feature. We wanted to see, was there any relationships we'd otherwise expect, for example, between blood pH and PCO2? And this is where some of the things start to fall apart as physiologic adaptations start to take over, because our bodies want our pH to be 7.4 no matter what. This relationship, roughly linear as they otherwise expected. The lower your pH, the higher your CO2 should be. And there is a linear relationship here. It's not a strong association with an R squared of 0.38. And you see the truncation there again, because the machines would not record a value higher than that. This was surprising at first. The relationship between minute ventilation, how much you're ventilating every minute, and your pH should be such that the lower my minute ventilation, the lower my pH. Like if I retain CO2, my pH should fall. And that wasn't seen here. And again, this becomes, you see the clustering in the upper left near 7.4, regardless of minute ventilation, essentially. And this is largely because humans adapt, and we're amazing physiologic adaptation machines. And so this was our first sort of indication, well, maybe this data isn't going to have a tremendous correlation. Here, if you look at the respiratory rate and the CO2, again, you have a lack of correlation. Again, this is because humans respond and they adapt. We overall looked at all of the features we engineered on a massive correlation matrix here, as you see. They obviously correlate with each other, the diagonal. And then there was some correlations throughout. We weren't without hope that some of our features in engineering of those features might not relate to one another or be helpful. So we did continue to move forward. Some of our categorical features showed very small differences. So the minute ventilation ratio change, for example, and PaCO2 tension, there was some change here, although it wasn't as obvious or as different as you might hope. And these categorical feature re-engineerings happened over and over again, where we turned the ratio of the short and long-term trend into a direction of abnormality consistent with the clinical context in which you'd appropriate interpreted as a yes, no for 1 or a 0, and a threshold was set, as I implied or stated earlier, for a standard deviation above or below. We ultimately came to a label that was a categorical outcome that included the pH being less than 725, as I said it before, and greater than PaCO2 greater than 78. That led to an 8% event rate, not common, again, as expected, and it'll play into what I've done downstream here about to deal with the class imbalance. And interestingly, while we developed these from the data, again, looking to see whether you were a standard deviation above or below a certain value, these are standing heuristics in clinical medicine. The pH of 725 is what I was taught 30 years ago as something I would consider responding to. And it's interesting to see if the data just simply reflects clinical practice, or if clinical practice somehow intuited this is an abnormality that was important. We ended up with 14 features, 77 representing short-term averages of 10 minutes worth of data prior to the blood gas. So what was happening with that parameter right before, and 7 features representing a categorical outcome of yes, no for a change in that long-term trend over the short-term trend. We ultimately picked the models or the algorithms I mentioned, and I'll just highlight some of the outcomes here. Naive Bayes is a simple one to start for a supervised task, which is what we have here, right? We have a label. There's minimal or no parameters to optimize. It assumes conditional independence, which may not actually be true here, but we went with it anyway moving forward. It often performs better than expected. And here you see the first presentation of the problem, at least the problem we have in clinical medicine, which is models often, when you ask them to predict on the held out testing set for us, even if, say, you were just looking at a traditional logistic regression with odds ratios, even if those odds ratios look compelling and they're significant and their confidence intervals are far different than one, when you ask it to predict, especially when there's class imbalance, the positive class, they don't do great. So here, again, when the true no was no, it did pretty well. But when the true yes was yes, it didn't do so great, and it predicted no a lot. And if you're minimizing a loss function, this makes sense. If it only happens 8% of the time, you can be accurate 92% of the time by just saying no. And that's what you see coming up next with just a logistic regression. Is it got the no class right all the time, but it got the yes class wrong never. And again, it can be very accurate this way. It's probably the most common clinical application for a supervised task, especially in clinical medicine, and with much of what you read in the neonatal literature ends with a logistic regression and a table of odds ratios, an area under the curve. I just point, the solver I used here was liblinear, in case anybody wanted to know. Again, this continues to highlight the problem we have with things that are less common, even to the point of being rare, and utilizing the models that we develop for prediction, moving beyond just presenting an odds ratio table. I moved on to a random forest classifier. It often performs well. It's, this audience knows very well, but it's an ensemble method of decision trees. There are multiple hyperparameters to optimize, which I'll talk about in a second. Again, similar outcome here, which was disappointing. The no class right all the time. The yes class right very little. Why this matters is I don't really need somebody to tell me that you're not the kid who's going to have a bad blood gas. I really need you to filter the noise out and tell me, yeah, that's the kid you should go look at. If I'm supervising the care of Nemours' NICU this morning, I think had 34 kids, half of whom are intubated. I need someone to help. I need a computer to help me figure out which is the baby I should go pay attention to, which is the baby whose blood gas is going to be poor the next time it's drawn. The reason that matters even more is we don't do blood gases very often. We're not continually surveilling this data point. And so it would be great if the ventilator could tell us this information. And again, here we could not do that. Even with tuning, the 3 parameters I mentioned previously, we didn't get much better. The yes class is still reported no all the time in the held out testing set. And so this was a lot of effort to work through this, work through tuning the hyperparameters. I think it's an incredibly valuable part of it. It often improves model performance tremendously. This was all done, this part of the work was all done in Python. And so all the Python code that goes into that and working through a grid search to find the best parameters. And we were still disappointed. You can imagine in real time as you're going through this and you're thinking, all right, now I'm going to tune the hyperparameters. It's going to radically improve performance. And you still end up performing poorly. It also, I think, points to the importance of asking these questions as we move forward with the science we produce, of saying not just what was the accuracy and mean area under the curve, because if you think back to the logistic regression results I showed for the definition of BPD, they weren't the best performing area under the curve for both of the predictions we used was 0.78. And so I think we really do have to move beyond that. That's at least my opinion, and really start to look at in the testing held out, what was the confusion matrix? Did you get what you'd hoped for? Which here on this one, I'll stop and say should have been a diagonal, right? You wanted to see 262 no, 23 yes along the diagonal. And we don't get there, obviously, but you try. So I took it one step further and tried to do a combination and add interaction terms through a combination of polynomial features, and then select the k-best select k-best in Python to select the 20 best performing features. Again, really not that much improvement here. Even with the random forest classifier, again, when I came upon this, I remember coming upon it the first time and looking through the path and the pipeline to develop, being super excited to then ultimately be disappointed that I really wasn't improving the minority class prediction. And so I kept pursuing that. It turns out that in the hyperparameter tuning you can do within random forest classifier pipelines in Python, you can ask it to wait for class imbalance. And this was the first time I saw, hey, you might be able to do this better. And I worked through this with the Python coding to do an iterative search through class weighting to find the optimum balance. And it does exactly what you'd think. As you change the weights for class imbalance here, you get worse at predicting the no class, but improve the prediction of the yes class. So you see there's a much improved performance here on the back end using class imbalance just within the function call to the random forest classifier in Python. This is probably, if you were going to apply this clinically, not that useful either, because now you're having too many false positives, right? The false positive right here, the accuracy is about the same. The area under the curve gets worse. But if you got called, out of these, I'm doing the math right now, 98 times, 83 times it was wrong, you'd quickly have alarm fatigue in the clinical setting. And so this, while demonstrating the importance of putting class imbalance in the fore of your mind when trying to balance these hyperparameters, didn't really lead me to something where I was like, yep, and now this is going to be a useful alarm. I then moved on to something called synthetic minority oversampling technique, which I'll talk about here for a second. It oversamples systematically via algorithmically from the minority class. It allows for the creation of a balanced data set to train on, and typically improves decision boundary identifications. You have to avoid leaking training data into testing data, which I did not do the first time I did it. And if you're wondering, if you leak it, how well does it do? It does great. And it almost seemed miraculous. And so as I got together, we had like weekly meetings and you're reporting. And I remember that meeting because everybody was like, you blew it, got to go back to the drawing board. You clearly didn't do that well enough. It essentially uses a k-nearest neighbor approach to sample from the minority class and extrapolates a new member of that class for each data point along a line between the neighbors. This, I believe, is one of the original, if not original, references here to Dr. Chawla's work, published in 2002 in the Journal of Artificial Intelligence Research. And so that technique has now been built into numerous packages that are available in Python and R. I did all this work in Python. I could have repeated it in R, so chosen. I've kept it in Python as I've developed it a little further, simply because I did all the work in Python. But it is one of the benefits is that it's been built into a variety of packages in Python and R. It is not a simple duplication of members of the minority class, and so it likely reduces overfitting, and it certainly is an improvement over that. The technique may make noisy data more noisy, and the created samples may actually not be physiologically possible for my example here. And if your data set is entirely categorical variables, which mine is not, but it's something I had to consider, it might not be well suited for that. So what was the outcome when I applied it? I applied the SMOTE algorithm in with a random forest classifier, which, because it had been sort of the best and I was most hopeful for a random forest classifier. And here we got simply better results, although still not what we would hope. We iteratively searched through class weights. We had used oversampling from minority class here with the SMOTE algorithm. And here you see something that starts to get much more useful for the clinical application that would be desired. You still have, not a tremendous over-reporting of false positivity. The accuracy falls, the mean area under the curve is improved slightly, the recall improves. It's not what you'd hope. I would love the true positives that would be reported at a much higher rate. Here you'd have fewer false alarms with this approach. And it definitely was the approach to hyperparameter tuning that held the most promise. And I think it is my preferred oversampling technique moving forward. As I end in the sensitivity of time, and just in the case there's some questions, it was really disappointing to me overall. I mean, I did take a set of features that were modest in their associations to begin with, and so it may be that the current ventilation data being collected is not adequate to potentially predict such things. It may also be that physiologic adaptation, as patients work quickly to reestablish normal physiology, defeat even the observations we're making at the bedside, even this rapidly. I would hope to identify all of the positive class while minimizing false positives. We did not do that. There would be a lot of not generating alarms or a lot of over generating alarms and false positivities. It did demonstrate that we were able to do it, though. We were able to get the data back from a clinical data warehouse. We were able to feature engineer it. We were able to use machine learning techniques to move beyond just simple odds ratios from a logistic regression. And it was incredibly illustrative and educational for us. I do think that healthcare systems are rapidly putting in place ways to collect high-frequency data. At Nemours, we have implemented ediometry, which is already a clinical tool that we're using at the bedsides in our ICUs to visualize heart rate, respiratory rate, and laboratory data layered on top of that, which is already showing tremendous interest from our clinician colleagues. It is storing it on the back end for anybody interested in utilizing the data. And other institutions like CHOP, where I left, have picked a different vendor called SickBay, but with much the same implementation and desire to be able to have access to this data. And that was largely the point of the project in the beginning anyway. It was interesting to explore increasing the dimensionality of the data and interaction terms, but it didn't really improve this approach. I think the class imbalance approach, again, as I stated previously, showed the most potential benefit. I think there's maybe better ways to feature engineer. And if I was going to start all over, I would probably propose, and I'm doing this currently with one of my friends, propose a deep learning approach instead of a supervised learning approach. I do think if you are going to approach a data set like this, oversampling from the minority class is a potential win, especially if it's even more uncommon. I think downsampling is another approach, but you lose a lot of data that way. I think I don't have it in this talk because I haven't finished working on some of it, but other supervised machine learning approaches might be best at yes. And like I said, the boosted tree models are being worked on currently. With that, I will end and hope that that was helpful, and people thought it was useful to hear, and take any questions if there are any.
Thank you so much, Kevin. This was great, very informative and very, yeah, very, very, very informative. So, any questions from the audience? Don't see any at this point. So, where are you picking this work now? You said you were exploring both deep learning and another supervised machine learning method. Is this correct?
Yeah, so I think the other two major supervised machine learning methods that I see in the literature are often a support vector machine and a boosted tree like XGBoost models. And I'll apply them as well to complete it to see if they would potentially do better. I don't know that they will because potentially the feature set here just is too poorly correlated with the outcome that was chosen. I think if I was going to go back and do it again, and I don't know that we even have the data available. There was limitations in the data available that were written to the Hadoop cluster from the methodology chosen to capture the data originally. I have a friend who has recorded pulse oximetry data from a group of infants, similar, non-invasively supported through the home setting. And she has data, she should have data every second for months of their pulse oximetry data, and she followed them until they were 2 years of life. I think with that sort of frequency for any one of these individual parameters, I might say that the feature is simply the pulse oximetry value every second. And so like you can imagine a data set where each patient's a row and each column is a second. And each second, and so there'd be 10, I did the math, there'd be about 10 million columns for our patients. But with that feature set, if you normalized it, you could potentially then just use a convolutional neural network or a long short-term memory neural network and say, can you identify based on this, with the plausibility being that babies who are going to be developmentally delayed and have poor outcomes when they're 2 don't control breathing very well and desaturate often. And so you could imagine just setting a deep neural network, a deep learning approach, and a CNN or LSTM to the task of a binary classification with that. And you don't have a minority class problem there. There's a lot of developmental delay in this cohort, unfortunately. So I've explored, like, if we had better data with this data set, would you go back and do that? And like if I had every second and parameters, would you just have a massive data set? You'd run out of memory quick. And that's one thing to potentially consider, is that as we collect these features about us at a physiology level, do we have enough memory? We think our current limits are big, and they are for much of what we do. But I was referencing the HERO score and the heart rate characteristic group at the University of Virginia, and I was speaking to the youngest member of their group about presenting at a conference for us in the winter, and she was saying that even for them, they histogram feature engineer the heart rate characteristics, because you might have a heart rate characteristic at the level of millisecond, and it gets pretty memory intense pretty quick. So those were the two things we've been considering, but approaches. But yeah, I think one of the limitations is we just didn't feature engineer well enough, and we need to do a better job. But there's a lot of work to come to the conclusion of I should have done it better to begin with.
Right. And so I think you alluded to, but the issue of the independence of the observations.
Yeah,
and
sure.
How do you handle this? I mean, how would you handle this, or is there a way to handle this, or is it important, or what do you think?
I think I'll start backwards with, is it important? It may not be important because we have a physiologic response to not having enough ventilation. And that response is the same within patient and within an individual and across individuals. And so it is very much an individual response. Now, there may be important cofactors not here, like were you sedated, were you able to breathe, were you not able to breathe? In neonatal medicine, we don't sedate babies that are ventilated, which is radically different. And we don't paralyze you away and take away your physiologic response almost ever. And so that gives us a different level of approach. Simply, we could include you as a variable, right, as a covariate, that this comes from patient 1 versus patient 2, and then include that in the models, like you would do for center, for example, if you were doing a multi-center trial, and then show that that doesn't have any impact on the correlations or the features, or it might. I think that would probably be the simplest approach when you're using the supervised machine learning methods, and how you would approach it in logistic regression is include the patient as if they were their own center. And then approach it that way, approach it with repeated measures techniques, and just inform the model that way. I think they would be the best ways to do that. But I don't know that it actually will matter, because I think the responses are the responses, and that where you are right now is independent of where you've been.
Oh.
Right. These events are probably, are they a Markov chain, right? Or do you have conditional independence of where you've been? Like when I ended up here and I didn't have enough ventilation, I responded with increasing my respiratory rate, regardless of how I've been in the past.
Oh, I see. That's interesting.
So it's conditionally independent of where you've been before, which is the requirement of a Markov chain.
Right. All right. Oh, this is really fascinating. I love it. Fascinating. Any questions? Oh, someone I cannot
I
see.
have one question, Claudia.
Sure. Yuchen, go ahead.
Yeah, definitely. Thank you so much, Dysart, for sharing your journey about the model development. This is amazing talk. I enjoyed it a lot.
Thank you.
I'm currently a data scientist at Christiana Care, and I actually worked about 5 years in CHOP. So it's good to see the CHOP and also the CTW, like the data warehouse name. So what my question is, you mentioned in the parameter tuning process, there were at first about 68 features, and then you were able to select the 20 best features. Can you elaborate more about that process, and also how do you balance out the clinical experience of understanding of these features and also what the machine tells you about the best selected features?
Yeah, so the original features that the ventilator was essentially just dumping to the clinical data warehouse, right? They are set by Draeger, the company. That is just what is coming out the back, right, through the Ethernet port, and that connected to the head wall medical device integration box, and we were able to capture. And that was the first sort of meeting was, well, what's in there? Like, what was it even saying? And so the first feature selection was just experts with domain expertise going, that value is not helpful to me. So for example, the set inspired fraction of oxygen, if you're looking at minute ventilation, so the combination of respiratory rate times tidal volume, as it is comes together to mean your minute ventilation, it was like, well, all right, well, I'm not going to use that, because while I can connect the two clinically, I'm not going to pay attention to it. So then you started to say, all right, well, the peak inspiratory pressure is there. Is the peak inspiratory pressure important? And so then there was a lot more, you can imagine, distribution plots for sanity testing, right? Like, is the value there? Is it complete?
Right.
Was it, yeah, it's there, but it's the least well-reported variable versus it's the most well-reported variable. There are some things that are measures from the patient that were reported through the ventilator. So like the ventilator can both sense the set ventilator rate. Like when we go to a ventilator, we say, we want to give you 20 breaths a minute, but it can also assess how many breaths you're really taking. So monitoring your respiratory rate. So it's like, well, do I want the set number or do I want the, and so, you know, there was a lot of that just moving through with domain expertise. And that might be one of my biggest pitches I'd include right here, is that I really do think that teams are super important, and that you, Chen, and I would be on a team and can talk to each other. And, you know, so I do think that people who are clinicians who spend the time are valuable if they can do some of this work, because then we can help talk to you better, you, Chen, right? Like, I'm sure you've had some conversations with clinicians, and I don't know that there's any clinicians on the call, so we can throw them under the bus. And you're like, oh, you don't know what I mean, do you? You don't even know what I'm talking about. And there's not a magic number somewhere. But anyway, so I think teams are super important. So we like parsed it down just with domain expertise first. For the one iteration of hyperparameter tuning where we used some programming skill to both first explode the number of features. So that's what we did first. We first said, okay, well, I think we ended up with like 115 or something features, once exploding them through interaction terms. And then individually went through and searched for, well, which ones were the 20 best at the top of the list for univariate correlation with the outcome. Does that make sense?
Yep.
And then we picked the 20 best. And of those 20 best, 16 were interactions, 4 were the original undisturbed values.
I see.
Then put them back into the model. You know, put them into the algorithm and use those 20 features instead of the original to come up with that. So that was the pipeline there. And like every good developer, you know, you go to Stack Overflow and YouTube videos for how to do things. And it's amazing when these YouTube videos hit. And I found an amazing example that walked me through how you might approach that. It ultimately didn't improve the positive class prediction very much, but it was a fun path to go down for a month or so and figure it out. And I think even though ultimately it's a negative study, really, like I didn't come up with the holy grail of the new ventilator alarm that tells me I should get a blood gas today, because that's the problem. Clinically, the problem is, just so everyone knows, I'll come in I'm on call Sunday. I'll come in call for Sunday morning. We'll get a gas once a day, maybe. Sometimes once a week. And like, it might be really bad that morning. And you're like, well, how long's it been bad? Right? And then when you talk to the nursing staff at the bedside, they'll say, oh yeah, the baby's been tachypnic for 2 days. I bet. You know, and so that's where I would love to bring to ventilators better alarms. Like, hey, this isn't right, and this isn't right, and this isn't right. You might want to get a gas because it's going to be wrong. So I hope that answers your question of how we feature engineered up and then parse down. And we used a K-nearest neighbor approach actually to identify that through the grid search.
Yeah, thank you so much.
And reduce the dimensionality again.
Yeah, thanks for the answer. That's great. Thank you.
I was muted. Any other questions from the audience? All right. Well, if none, thank you again. This was really informative. And everyone, please keep in touch, and we'll have other speakers aligned soon. So thank you again for being our first speaker this year. This was really wonderful.
Yeah, thank you so much for having me. It was really an honor, and I hope I didn't embarrass myself.
No, you didn't.
All right. Well, thank you. And if anybody has any suggestions for me, please email me. I'd love to hear them. And have a great day.
All right.